Got a lot of things to talk about, beginning with concavity of a function. And we know what it means if a function is concave up, like this quadratic is. All right? But what I want you to see here is the relationship that happens in terms of calculus with concavity. This function is x squared. All right, I know I've got it offset to the side, but let's just say it's our regular old x squared function. What is the derivative of x squared? F prime of x is 2x. Now, if I were to graph the derivative, isn't 2x something like this? Okay, here's 2x. So I have a question for you. On the entire domain, is 2x increasing or decreasing? It's increasing. Okay, this is increasing. One other thing. The first derivative is 2x. What's the second derivative? 2. Is that positive or negative? Positive. And what I've just done is I've led you into a couple of our tests for concavity. All right, let's get to it. We'll call these tests for concavity. Number 1. F is concave up if f prime is increasing on an interval. Which we just talked about, relating x squared and 2x. All right. Secondly, f is, and let's just put c dot u dot, concave up, on an interval where the second derivative is greater than 0 or positive. So a function is concave up if f prime is increasing on an interval. It is also concave up on an interval where the second derivative is positive. The opposites of this are true. Okay? So, I don't know, I guess for the sake of time, we'll just say concave down if f prime is decreasing. We'll try to save ourselves some writing here. And concave down if the second derivative is negative. Okay, save ourselves a little bit of writing there. So, if we're talking about concavity, okay, let's look at an example here. Let's say that I had 3 plus sine of x on the interval 0 to 2 pi. Now, first off, let's just kind of do a little quick sketch of this function. Isn't this just the sine function moved up 3 units? 1, 2, 3. So instead of starting at 0, it's going to start at 3. All right? And instead of going up to 1, it's going to go up to 4. Instead of going to negative 1, it's going to come down to 2. So it's basically going to stay sandwiched in between 2 and 4. Okay, that would be its range is from 2 to 4. All right, and of course this over here is my 2 pi. This right here in the middle is my pi, just like before. And if I wanted to talk about concavity of this, well, isn't it obvious to see where it's concave up and concave down by looking at the graph? But we need to do this analytically now. So let's take the derivative. Okay, the derivative of this, f prime of x, well, the derivative of 3 is 0. The derivative of sine is cosine of x. Now, what is the second derivative? Let's just go ahead and do that. Good job. The second derivative is negative sine of x. Now, didn't we just say, let's come back to our summary screen, it's concave up where the second derivative is positive, right? I think it's going to be easier to look at the second derivative. So, don't we know how to graph this thing? Isn't that just the sine function, but it starts down instead of starting up? So this function is just going to do this, okay? Instead of going up, it's going to go down. This is still going to be 2 pi. This is still going to be pi. And remember what this thing is. This is the second derivative. This is the graph of the second derivative. All right? So now we have to ask the question, where is the second derivative positive and negative? Well, isn't it negative here, and then it's positive here, right? So we just need some intervals now. It is negative f double prime is negative on from 0 to pi. So if it's negative, what is it? Concave up or concave down? Concave down. So it is concave, if I could write here. Come on, Mimeo, you can do it. Concave down. And the second derivative is positive from pi to 2 pi. It's positive from here to here. So the second derivative is positive on pi, or from pi to 2 pi, and that's where it is concave up. And if we look at my original function, didn't that work out? Doesn't that make sense? Look at my original function. Concave down from 0 to pi, concave up from pi to 2 pi. Now, there's a special little place that we have not learned about yet, and I know you're excited to learn this. The place where the concavity changes. I need a pretty little color for this new thing. This place right here, where the concavity changes from concave down to concave up, is called a point of inflection. Inflection, not infection. So let's, on a new page here, let's write what this point of, some people might like to think it's a point of infection, but a point of inflection is a place where the concavity changes. Either from concave up to concave down, or vice versa. Okay? So, how do we find a point of inflection? Well, let's come back for a second. Didn't we say that it's concave down when the second derivative is negative? and it's concave up when the second derivative is positive. So what we really need to know is the 0. So to find the point of inflection, all right, set the second derivative equal to 0 to find the points, sometimes it's going to be points of inflection. I'd put a big box around that. Seems like, for whatever reason, people forget how to find points of inflection. All right, let's do an example, all right, of finding some points of inflection. If you're asked to find, and I'm just going to put POI, find the points of inflection for f of x equals e to the negative x squared. That's a good ugly function for us to work with. So let's go ahead and tackle it. First thing we've got to do is find the derivative. Believe it or not, that is not always your first step in life, but in this case, a lot of times it is in calculus. Find the derivative. So the derivative of e to ms is, we use the chain rule, it's e to the ms times the derivative of the ms, which is negative 2x. Now, if we're talking about points of inflection, I need the second derivative. So now I'm doing the derivative of this, which, it's a product. So if I do the derivative of this, I have to use the product rule. Okay? So the second derivative, I have to use the product rule. The derivative of the first function, this is my first function, is the same thing. It's e to the negative x squared times negative 2x. There's the derivative of the first times the second the way it is, which is negative 2x, plus the derivative of the second function, which is just plain old negative 2, times the first function the way it is, e to the negative x squared. Now let's clean that up a little bit. Yes, it's still ugly, but we can make it look a little bit better. It's going to be 4x squared e to the negative x squared minus 2 e to the negative x squared. And already it's not quite as ugly as it once was. Now, remember what we're going to do? Are we going to set this equal to 0? And if you remember one of the tricks I told you, anytime I'm setting something equal to 0, it helps me if I can write the algebra expression as a product. So do you see something that I can factor out of both of these? Good. Very good. I can factor out an e to the negative x squared. And I'm left with, actually, can't I factor out? I can factor out a 2. I'm sorry, I missed it. 2. So I will be left with 2x squared minus 1. And that is equal to 0. And now I have written this as a product equal to 0, which means I can split this up into two handy-dandy equations. 2x squared minus 1 equals 0. And 2e to the negative x squared equal to 0. Okay? I'll work on the left side in a minute. Let's work on the right side because it's easier. I would add 1 to both sides. So 2x squared equals 1. So x squared equals 1/2. And if I take the square root, I find out that x equals plus or minus the square root of 1/2. Don't worry about rationalizing it right now. That's what it is. Now the other side, we're a little bit more worried about that, but we don't need to be. Let's go to a new page. 2e to the negative x squared equals 0. First thing I would do is divide both sides by 2. So I have e to the negative x squared equals 0. Okay. And I have a negative exponent, so wouldn't this be 1 over e to the x squared equals 0? Now, let me ask you a question. Let's look at this function. Before we go any farther, I have e to some power, and that power is x squared. So isn't this power right here always going to be positive? So don't I have 1 divided by some number, right, raised to some power, whatever that power is? Can that ever be equal to 0? No. Another way that you could tackle this problem, everybody, is you could take the natural log of both sides. Right here. If I took the natural log of both sides, I'll still come to the same answer. I can't take the natural log of 0. It's not in the domain. Okay? This is a problem. So there's nothing, there's nothing here on this side right here we can say does not exist. But I still have 2 points of inflection. Okay? And so my answer then is, I need a new page. My points of inflection are x equals the positive square root of 1/2 and the negative square root of 1/2. And if we were to graph this, we're not going to turn on the graphing calculator right now, but I can tell you that the graph of my original function looks something like this. Only I think it's centered right at. Should be centered right there. And if you look here, here is the positive square root of 1/2, and right there's our concavity change. And here is the negative square root of 1/2, and there's our concavity change. All right? Points of inflection. Set the second derivative equal to 0. Now, I have some more good news for you today, and that is an even easier way to find maximums and minimums, and that's the second derivative test. The second derivative test is, I believe, a lot of times easier. Now, it does involve working with the second derivative test, or finding the second derivative, but I think a lot of times it's easier. Let's make a big note up here. Second derivative test for finding maximums and minimums. Okay, we've done the first derivative test. Now we're going to do the second derivative test. So we have a theorem here. Here's our theorem. If f prime of c equals 0. Now let's stop right there. Do you remember what we called those? Begins with a C? Critical points. Okay? So you find your critical points first, right? If f prime of c equals 0. So here we're thinking critical points. All right? If f prime of c equals 0, then I know two things. Number one, if f double prime of c. So now you're going to take one of those critical points and plug it into the second derivative. If f double prime of c is negative, let's put a big, so for whatever reason, when you write less than 0, people don't always get that that's negative. But if f double prime of c is negative, or you can just put a big minus sign, if that is negative, f has a max at c. It's the opposite of what you would think it is. That's the way I remember the second derivative test. You would think if the value of the second derivative at c is positive, it's a max, but it's not. All right? So the way I keep that straight is I remember that it's the opposite of what you would think it is. And then number 2 is true if f double prime of c is positive, then f has a minimum at c. Okay? So let's do an example of this so that you know how to work the second derivative test. Let's say that my function is x cubed minus 12x minus 5, and we want to find the extrema. And we want to use the second derivative test. Okay? Well, the first thing we need to do is find our critical points. All right? So to find our critical points, we always start by finding the first derivative, which in this case is 3x squared minus 12. I always find the first derivative. I always set it equal to 0. 3x squared minus 12 equals 0. That thing is going to solve real easily. 3x squared equals 12. X squared equals 4. So x equals positive 2 and negative 2. Those are my critical points. Now, I know this function is easy, okay? But the process is the same, all right? The next thing I need to do is find the second derivative. So the second derivative is going to be 6x. All right? Now watch how easy this is. Once you've found your critical points, you remember how before in the first derivative test you have to check values to the left and the right and do all. Well, look at this. Once you have the second derivative, all you have to do is plug these in there. And it'll tell you if they're max or min. So f double prime of 2 is going to be 12, which is positive, which means x equals 2 is a minimum. Remember, it's the opposite of what we think it is. And then I find f double prime of negative 2. I find out that that is negative 12. So that is negative. So x equals negative 2 is a max. I think the second derivative test is easier than the first derivative test. The one thing that you have to consider, though, is sometimes finding that second derivative is a little bit hairy. So it's not always faster, but most of the time it is. Something else. These are the x-coordinates of the minimums. How would I find the actual minimum or maximum value? You would have to plug it into the original function to get the actual values. Don't forget that. This is just the x-coordinate And let's actually do that just to kind of keep our skills sharp. All right? Let's find those maximums and minimums. F of negative 2, let's see, my function is x cubed minus 12x minus 5 is my original function. I'll change my color here in a second. So if I want to find the maximum value, I plug in negative 2. So that will be negative 2 cubed minus 12 times negative 2 minus 5. That's going to be negative 8 plus 24 minus 5. 16 minus 5 is 11. That is the actual maximum value. Or I could say the maximum occurs at negative 2, 11. That's the actual ordered pair for where the maximum value occurs.
So that 12 isn't your...
So that 12, yeah, from the previous page, this thing right here is not the minimum value. All we're using that for is to get a sign.
Okay.
That's the only thing we're using it for. To actually get the maximum value, you have to plug it back into your original function. Same thing for the minimum. If I wanted to find the minimum, I would do f of positive 2, which would be 2 cubed minus 12 times 2 minus 5. I'm going to tell you that turns out to be negative 21. And so your minimum value is actually positive 2, negative 21. Okay? So, what if, one last thing that we need to talk about real quick is you're going to see some problems where they give you the graph of f prime of x. And let's say that your graph looks something like this. Let's say that this value right here is negative 2. This value is 1. This is 4. Something like that. Now, let's say that they asked you, where is f increasing? Where is f increasing? Didn't they give me the graph of the derivative?
From negative 2 to 1 and from 4.
So what we need to think of here is we need to look at function values. Isn't it positive here?
Oh, yeah.
Isn't it positive here?
Yep.
It's negative here,
Yep.
and it's positive there.
What about the 0?
So if the value of the derivative is positive, doesn't it have to be increasing? So we could say that it is increasing from negative infinity to negative 2, and we are breaking it up because that's a 0 there. Union, it's increasing from negative 2 to 1, union, and it's also increasing from 4 to positive infinity. All right. Where is it decreasing? That's easy. It's decreasing from 1 to 4. Now, how about extrema? What if they asked you for where's the maximums and minimums just from what they've given you here? Well, remember how we find those extrema. Don't we look for critical points first? Aren't there 3 critical points? Those are the 3 places, right, where the derivative is equal to 0. So if I was looking for extrema, I really do have enough information here. Now, I can't use the second derivative test, but I can use the first derivative test because look at this critical point. It's supposed to change from positive to negative or negative to positive. Well, guess what? X equals -2 is not an extrema because the value of the derivative to the left and the right have the same sign. But when I get to 1, the derivative changes sign from positive to negative, so 1 has to be a maximum. X equals 1 has to be a max. What would 4 have to be? X equals 4 is a min. And we will stop there for today.